If you've been looking into the numerical methods used by CFD codes, perhaps as part of your PhD or master's thesis or technical report, then you may have come across the idea of Rhie Chow or Rhie Chow type interpolation methods and checkerboard oscillations. It's often not clear and not well explained online and in various research papers what this type of interpolation actually means and how it's applied to CFD codes. Well, what I'm going to be doing for you here is explaining in detail the phenomenon of checkerboard oscillations and Rhie Chow type interpolation and staggered grids, because these form a real foundation for how CFD codes were developed over the past 40 years. And what you're going to get from listening to these videos is a deep appreciation for how and why CFD codes have been developed the way they are. And it's really going to help improve your understanding and your literature review sections that you use to write your reports. So I know you're going to gain a lot from this series. It's going to be really interesting and probably isn't material you've come across before in your day-to-day CFD knowledge and CFD understanding. And as it's quite a broad topic and it's quite detailed, what I've decided to do is to break it into 3 parts. And in the first part, I'm going to be looking at the phenomenon of checkerboard oscillations themselves. And then in part 2 and 3, I'm going to be looking at methods which CFD codes use to alleviate and suppress these oscillations. And one of those methods is often called Rhie Chow or Rhie Chow type interpolation, after the 2 authors who proposed it back in the 1980s. So I know you're going to get a lot of information from this talk. Let's press on with part 1, which goes through the phenomenon of checkerboard oscillations and how they occur. So the focus of part 1 of this lecture series is going to be on the phenomena of checkerboard oscillations. We're going to be having a look at how they arise, and at the end we're going to look at what potential methods are there for removing and alleviating these checkerboard oscillations. Now, in order for us to understand checkerboard oscillations and how they arise, we're going to have to go back first and have a quick recap of the finite volume method. So that's how the talk's going to start. I'm going to first look at the finite volume method to bring everyone up to speed to where we are, and then I'm going to introduce and demonstrate where checkerboard oscillations arise from to finish off this part of the talk. So what we need to think about with CFD and the finite volume method is where we're starting. And we're looking specifically at the incompressible continuity and Navier-Stokes equations, and I've got those equations for you there on the slide. Equation 1 being the incompressible continuity equation, and equation 2 being the Navier-Stokes or momentum equations. And what I want you to notice in these set of equations that we're looking at is that we've actually got a total of 4 equations. We've got 1 continuity equation and then 3 momentum equations for u, v and w. And we've actually got 4 unknowns as well. We've got u, v, w and p for pressure as well. So we've got 4 equations and 4 unknowns, and the equations are of course coupled together, but there are some difficulties in the incompressible continuity and Navier-Stokes equations when we try and solve them. And the primary difficulty is, if you look closely at the equations, there isn't actually an equation for pressure. What we've actually got is the 3 momentum equations provide 3 equations that we can solve for u, v and w, and then the solution to those equations, u, v and w, has to satisfy the continuity equation. So the continuity equation actually acts more as a restriction on the computed velocity field rather than an additional equation that we can solve. So if we were to solve the 3 momentum equations, we'd have a solution u, v and w in all the cells in our mesh, but for that solution to be valid, it would have to satisfy the continuity equation in each of those cells as well. And this presents some difficulty to us when we're putting together a CFD solver, because there isn't an obvious way that we'd calculate the pressure field. And we need the pressure field because the pressure field provides the pressure gradient, which is one of the driving forces in the momentum equations. Now, many of you, of course, would think, why don't we use an equation of state to calculate the pressure field? Why don't we use something like the ideal gas law, for example? Well, because we have an incompressible problem here, the changes in density are relatively small, and so we can't use those changes in density to allow us to calculate the pressure field and changes in pressure. So what we have to do is we have to come up with some very careful algorithms that will allow us to solve the incompressible momentum and continuity equations in this form. And these are often called pressure-based solvers by some CFD codes, and you may be familiar with some of the algorithms that have been developed to solve these equations, algorithms like the simple algorithm. And for this talk, we're not going to be focusing on those algorithms. We're not going to be focusing on the pressure-based solver or simple algorithms or piezo algorithms, for example. What we're going to be looking at here is specifically the phenomenon of checkerboard oscillations and where they arise. And the first thing to understand with checkerboard oscillations is that they arise as part of the discretization of the momentum equations. So in their continuous form as they were presented on the previous slide, the momentum equations aren't going to result in checkerboard oscillations. The checkerboard oscillations arise when we discretize those equations depending on the method that we use for discretizing those equations. So for this set of talks, in order to understand checkerboard oscillations, we need to first go through the discretization procedure. So then we can highlight what are the specific stages that cause checkerboard oscillations to arise. And so that's what I'm going to do in this first part of the talk. I'm going to be quickly going through the finite volume method and using it to discretize the momentum equations so you can see where the checkerboard oscillations arise from. And for simplicity here, I'm only going to be looking at the steady state case with no source terms. Therefore, just leaving left behind the terms we're going to look at are only the most important ones that directly result in the checkerboard oscillations arising. And if you're interested in the full unsteady set of Navier-Stokes equations and perhaps the cases with additional source terms, I've linked in the description below a very useful paper which you can use and follow along, and it will go through the full treatment using much of the same notation that I use here. But for the video, I'm just going to limit it to the steady state case. And the steady state case, what we're going to be doing is looking at equations 3 and 4, which you can see there in the slide. And of course, the unsteady term in the momentum equation on the left, we're not considering that, so that's gone. And the source term S on the right-hand side of the momentum equation, that's also gone. We're not considering those terms. And the other thing I want to point out before we actually get stuck into the maths and the derivation is just to recall that there are 3 momentum equations. We've got an equation for U, that's the X velocity component, V, that's the Y velocity component, and W, which is the Z velocity component. And what I'm going to do for this talk, again for simplicity to make it crystal clear, is only to consider the U momentum equation. That's the velocity in the X direction. And so the notation and the form I'm going to use for this derivation, you can see there in equation 5. And this is a single equation for the X velocity component, which we're calling U. And so what I've done to get to this equation is dropped the subscript J that you will have seen in the previous set of the complete momentum equations, which will give you equation 5. And you can see the unknown is capital U, the X velocity. And the other thing I'm doing here to really follow along and be consistent with the paper that I've linked in the description to this video is I'm using tensor notation, which uses the Einstein summation convention for expressing these partial differential equations. And just as a reminder, many of you will have seen this before, but what the Einstein summation notation indicates is that if you have 2 indices that are the same, in this case I and I in the same term, that's shorthand for summation over those terms. So for example, on the left-hand side of the momentum equation, the convection term, rho partial u ui over partial xi, that's shorthand notation for what you can see there in equation 6, where the summation is over the index I, and of course you go through the 3 velocity components u, v, w, which correspond with the coordinate axes x, y, and z in Cartesian coordinates. So that's just another flag here that we're using the Einstein summation notation, and we're just looking at the U momentum equation for simplicity. Now, once I've been through this derivation, you can of course just repeat that process and go through and do exactly the same thing for the V and W momentum equations if you want to do that. And the way we're going to proceed is now we need to discretize this partial differential equation. And the way we do that in CFD nowadays is most often using the finite volume method. And for the finite volume method, what we do is we consider a single cell in our mesh. So if you think of your computational mesh that you've made for your CFD calculation, we're considering a single cell in that mesh. And the cell could have any shape, any size, and be anywhere. But for a single cell, what we do is we integrate the partial differential equation over that cell, or the control volume as it's often called. And so you can see that in the mathematics, the way this is reflected is by integrating each individual term over the volume V. And you can see that there in equation 7. I've also moved the diffusion term over to the left-hand side of the equation, just for convenience in everything that follows. And the key stage in the finite volume method that really all of the discretization and the CFD codes are developed from is an application of the divergence theorem, or Gauss's divergence theorem as you may see it referred to. And with the divergence theorem, as a reminder, what we do is we apply the divergence theorem to the convection and diffusion terms on the left hand side there, and shorthand what we do is we replace the volume integral. So rather than integrating over the volume, we're now integrating over the surface of that cell S, which you can see there in the terms, and we've now got the unit normal vector Ni in there. And I've been through the divergence theorem in a lot more detail in my other videos on the finite volume method and in my courses as well. So if you've been through any of those, you'll be familiar with this now. And I don't want to go through the divergence theorem in too much detail because it's not the focus of this talk. But broadly, what you're doing when you apply it is you're saying that an accumulation of some substance or field within a volume must be equal to the flux of that field over the surfaces of the volume. So you can think of this as a box with some balls inside it. And if you add balls to the box, the total number of balls in the box increases. That's the volume integral. But the rate at which it increases in the volume must be equal to the number of balls that you add into the box over time. That's really all the divergence theorem is telling us. So we've got the underlying terms, convection and diffusion there in equation 8, expressed using the divergence theorem. And what we're going to do now is we're going to simplify each of those terms in the equation so we can arrive at a concise form of the discrete momentum equations that we can then use to demonstrate where the checkerboard oscillations arrive from. And the first term I'm going to look at is the pressure gradient. And the simple way of looking at the pressure gradient, you can see there in equation 9, is we've got the integral over the cell volume of partial P over partial X, the pressure gradient in the X direction. And the way that we simplify this term is to notice that, of course, in CFD, all of the flow variables, pressure, velocity, temperature, vary linearly across our cells and across the faces of our cells. And so if you look at the diagram there, what we know is we know the pressure gradient at the centroid of the cell at position P, the centroid, and what we want is we want the integral over that cell. Now, because the pressure gradient varies linearly across the cell, if you look at that diagram, the green area, what you'll notice is that the integral is actually the same if we just take the value at the cell centroid and then multiply it by the volume. So the area under the dashed line, which you can see there, equivalent to the value at the centroid multiplied by the volume, is actually equal to the integral over the straight solid line. You can see that as long as you take that value in the middle, it doesn't matter what the gradient is, the integral will always be the same. So that allows us to write equation 9, where we've replaced the integral of the pressure gradient over the volume with the pressure gradient at the centroid multiplied by the volume of the cell. And that's a very useful simplification that we use in the finite volume method, and we're also going to use a bit more in the derivation that follows. So we've looked at the pressure gradient term on the right hand side in equation 10, we've simplified that, and now what we're going to do is look at the convection and diffusion terms on the left hand side. And in CFD, all of our cells have a finite number of flat faces. That's the key thing to think about. If we have a square cell, then our cell has 4 flat faces. If we had a triangle, we'd have 3 flat faces. And it doesn't matter how many sides our cell has. If we have a polyhedral cell, it will always have a finite number of flat faces. So what we can do is that integral over the surface, where we'd be integrating our quantity over the entire surface, we can replace that integral with the integral over each of the surfaces in turn, and we then add them up. And that's how we move from equation 10 to equation 11. We integrate over, for the square for example, the top face, and then integrate over the side face and the bottom face and add them all up. And that integral of course will be the same as the integral over the entire surface, because we have a finite number of flat faces. And what's the integral over the face? Well, we can use that same trick that we used before with the pressure gradient, where we notice that because the flow quantity, whatever it may be, varies linearly across the face, the integral will be equivalent to taking the value at the center of the face and multiplying it by the area of the face. And so that's what we do to arrive at equation 12. You'll notice that that integral over each of the surfaces is gone, and instead what we've got is just the value at the face center, which I'm denoting with a subscript f, multiplied by the area of the face A. So we're doing a lot better now. Our integrals we've now got rid of our integrals, and instead we've got summations with quantities evaluated at the center of faces. We're doing a really good job here, and we've almost arrived at the discrete form of the U momentum equation that we can solve. And of course, you can appreciate that if you were to then apply this discrete equation to all of the cells in your mesh, you'd end up with a set of coupled equations, coupled algebraic equations, and that's what the CFD code actually solves when you're solving. But in order for us to get there, we need to do just a little bit more work. And the next thing is for us to notice that in CFD codes, the majority of CFD codes, we solve and evaluate the flow quantities at the cell centroids. So when you create your mesh and you pass that to the CFD solver, and the CFD solver creates a solution for you, what you're actually doing is calculating the value of velocity and temperature, say, at the centroid of all of your cells in the mesh, and then there's a linear variation between them. But what that means for us when we set up the equations is that we need the equations to be written in terms of the flow variables at the cell centroids. But for these summations that we just created, you'll notice that we've got UF, that's the x momentum or x velocity component at the center of the face, but not at the centroid of the cell. So we need to somehow convert the velocity at the center of the face to the velocity at the cell centroids. We need to rewrite it slightly. And then when we've done this, of course, we've got a set of linear algebraic equations in terms of the velocity at cell centroids, which we can pass to the CFD solver. And it's at this stage where there's actually a bit of flexibility in the finite volume method. And this flexibility is passed over to the user, where the user will often get to decide in the CFD code what method they'd like to calculate the values at the cell centroids from the values at the face centers. This is often called an interpolation scheme or a discretisation scheme. And if you've watched my videos before on upwind differencing, linear upwind differencing, you will have come across this concept before. We're doing exactly the same thing here. But for our example, if we were to choose linear interpolation or central differencing as it's often called, then we could write UF is just half the value of UP, that's the centroid on the left, and add half the value of UN, that would be the centroid on the right. And we could write this more generally, as you can see there in equation 15. We could say UF is equal to AP, where AP is some coefficient multiplied by UP, plus AN, which is some coefficient multiplied by UN. And we can see that if we just take values of a half, that would be fine for our linear interpolation or central differencing. Now, the reason I've kept it in this general form is the method of the interpolation scheme is generally kept open to the user. You may see this in your CFD codes where you get to choose, am I going to use upwind differencing or linear interpolation, for example, what scheme or discretization scheme am I going to use? We need to keep it general in the derivation that follows. So this is central differencing is one example. What if we were to use upwind differencing? Well, in this case, for example, if the flow was going from left to right in the diagram, then the value of the velocity at the face center, UF, would be equal to UP. We'd be taking the upwind value at that face center. Whereas if the flow was going from right to left, we'd be taking UN. That would be the velocity which would be upstream of the face in that direction. Now, regardless of whether we chose the linear interpolation or the upwind differencing, which I've shown you here, you can write UF as AP plus AN, where AP and AN, these are coefficients that will vary depending on what discretization scheme the user chooses. But for us setting up the CFD code, it's fine for us to use this form, equation 17, it's sufficiently general. And what we can do now is we can go back to that equation 18 and we're going to be replacing UF in the convection term by that AP, for example, which plus AN, which we just saw. And we can do a similar thing for the diffusion term there, which is the second term on the left-hand side. And of course, we may have to do some rearranging of terms and collecting things depending on what form we use. But in general, you'll see that for that single face we considered, we can arrive at equation 19. Equation 19 is sufficiently general, regardless of whether the user has chosen upwind differencing or central differencing. We can always write the convection and diffusion terms on the left-hand side as AP plus AN, where the N means neighbour, the neighbour face, and P is the standard convention we use for the centroid we're interested in. Now, I don't want to go into full details here about how you do all that rearranging and where the terms come from. I've covered that before, and if you want some examples of how to do that and have a go with it yourself, you can check out one of my fundamentals courses and you'll be able to see exactly where those coefficients come from and what value they take. But for now, in understanding the checkerboard oscillations, we just need to use equation 19. It's sufficiently general for us. And some of you may be looking at equation 19 and maybe thinking it's a little bit confusing. I can't really see what it actually means. Well, before I go on, I just wanted to do a quick reminder for you about what equation, in this case 20, actually means. And what equation 20 actually means is the left-hand side is telling us that we're considering the U momentum equation, and so what it's telling us is that the cells that surround the cell we're interested in may diffuse and convect momentum into that cell, and that diffusion and convection of momentum into the cell has to balance the pressure gradient across the cell, which is the right hand side of equation 20. So all of the fluxes of convection and diffusion into that cell must balance the pressure gradient across the cell. And we may have other forces acting on the cell. They would also be on the right hand side of that equation. And we often have a summation there on the left hand side to indicate that we're summing over all of the neighbors, because in the diagram there you can see the cell we're considering in green. It has multiple neighbors, and each of those neighbors can contribute some momentum into our cell through convection and diffusion. So this is really equation 20. To understand this talk, you don't fully need to be able to derive the form of equation 20 yourself, but if you look through the paper that I've linked in the description below and other sources in the internet, many places will start with this discrete form of momentum equation 20. So for your understanding, you can also be happy to just start with equation 20, and if you want to do the derivation yourself, feel free to do that. But we've now arrived at a point where we can now start to look at understanding Rhie Chow interpolation and checkerboard oscillations, starting with equation 20, and that's what we're going to do. But before we can do that, we're going to take equation 20 and do a bit of rearranging first, rearrange a few of the terms. And the rearranging you'll see is also carried out by other sources on the internet, but I'm going to go through this properly for you here so that you understand it. So if we start with equation 21, that's the discrete U momentum equation, remember. What we're going to do is we're just going to move that summation term, the summation of AN, UN, onto the right-hand side of our equation, or you can think of it as subtracting the summation from both sides. And then what we're going to do is divide both the left and the right-hand side of the equation by AP, where AP was that combined coefficient from convection and diffusion that we saw before. And now we arrive at equation 22. And we can see the maths is starting to get a bit confusing, but always remember that this is still just a discrete form of the momentum equation for that cell in the mesh that we're considering. And for us to follow along with the papers and the descriptions that you'll see in various textbooks, what we're going to do is to introduce some notation. And the notation I'm going to use is not chosen by me, it's consistent with the papers and the sources that you'll see. And what we're going to use is that summation term, minus 1 over AP multiplied by the summation of AN UN. We're going to call that UP tilde, and the little squiggle on top is a tilde, because you can see that that term still has the units of velocity, and so in some way it represents a velocity. And then the other term which we're going to simplify is that VP divided by AP, which you can see there in equation 22. And this is often called dP. So this is some coefficient which is equal to the volume of the cell that we're considering divided by that coefficient AP for convection and diffusion. And this allows us to arrive at equation 24, which I'd like to emphasize is still a representation of the discrete momentum equation. We haven't done anything different here. We've just discretized our momentum equation for the mesh, and that's the momentum balance, which you can see there. What's going to happen is the convective and diffusive fluxes into the cell are still going to balance the pressure gradient across the cell. And at this point, what we've done is fine and consistent. We're not going to be generating any checkerboard oscillations at this point, but now what I'm going to start to show you is how equation 24 can show us where the checkerboard oscillations start to arise from and why you might need to consider something like Rhie Chow interpolation. And to do that, what we're going to do is look at the pressure gradient term, partial P over partial X at the cell centroid P. And for simplicity here, even though we've got three momentum equations, U, V and W, I'm just going to present to you an example on a uniform 1D mesh. This is the simplest example and it's easiest for you to understand where the checkerboard oscillations are coming from. And so how do we evaluate this pressure gradient? How do we evaluate partial P over partial X? Well, if we think of our cell in general, the pressure, so not the pressure gradient, will also be varying linearly across the cell. And we've got PE, that's the pressure on the east face on the right hand side of the cell, and then we've got PW, which is the pressure on the west face of the cell on the left hand side of the cell. And what I've used here is I've used lowercase subscripts E and W to represent face values, and then I'm going to be using capital letters to indicate values at cell centroids, just to be consistent here. And the pressure gradient across the cell we could write quite easily as PE minus PW over delta X. Delta X is just the size, the width of that cell in 1D. And of course, many of you will notice and realize here straight away that even though we've written an equation for the pressure gradient across the cell, we're only calculating our solutions at the cell centroids. So clearly we need to do some further rearranging here. And the way we can do that, of course, is just as we did before, we can use linear interpolation or central differencing to write the pressures on the faces in terms of the pressures at the centroids of the cell on either side of the faces. And so we can use equation 26 and we can say the pressure on the east face is half the PE minus PW, and we can do the same for the pressure on the west face of the cell. And if we substitute those in to our equation on the previous slide that we had for the pressure gradient, what we arrive at is that the pressure gradient partial P over partial X at the centroid of the cell, so I've got the large uppercase P, which you can see there, is going to be equal to the pressure on the east side of that cell minus the pressure on the west side of the cell divided by 2 delta X. That's double the distance. And this is quite a subtle point, which we'll see in a minute can lead to checkerboard oscillations. It's this method that we've chosen to discretize the pressure gradient can lead to checkerboard oscillations if we're not careful. And don't worry, by the end of the talk we will have seen why this is the case, and you'll see where the checkerboard oscillations arise from. So for a minute, let's just think about the equation that we've derived here. We're saying that the pressure gradient at the centroid of the cell P is equal to the pressure at the centroid of the cell on the east of it, or on the right of it, minus the pressure at the centroid of the cell on the left of this cell divided by 2 delta X. And what you can see there in that equation is that the pressure gradient doesn't depend on the pressure of the centroid of the cell itself. So it doesn't depend on PP. And this is a problem. If you were to set up a CFD code in this case, you could quickly arrive at checkerboard oscillations. And what I'm going to do is to show you how those oscillations can arise. And it's important to note before we move on that it's not just the choice of the method used to discretize the pressure gradient, but it's also due to the continuity equation, which we haven't considered yet. And jumping back to the continuity equation now, as a reminder from the start of the talk, the incompressible continuity equation, you can see there in equation 28. And as before with the momentum equations, what we did was we used the finite volume method. So we integrated that equation over a cell or a mesh in the domain, and then used the divergence theorem on that equation. And that's exactly what we're going to do here for the continuity equation. So integrate equation 28 over the volume, and then use the divergence theorem to replace that volume integral by the surface integral. That's equation 29. And then once again, we use the same fact that we did before, that all the cells have a finite number of flat faces and the flow variables vary linearly across the face. And then this will allow us to take, rather than having that integral over the entire surface of the cell in 2D or 3D, we can replace that by the integral over each of the faces in turn, and then we can replace the integral over the face with the value at the face center multiplied by the area. And that's equation 30, which you'll see there. And what I want to do now is, rather than use equation 30, because equation 30 still has this summation and it still appears quite complicated, what I'd like to do is to just simplify this into 1D so that it's easy for us to follow, just like with the pressure gradient example we were looking at before. I want to simplify this continuity equation into 1D so it's really clear where the checkerboard oscillations are arriving from. And in order to do that, what I want you to do is just to consider one cell in the mesh, which you can see there highlighted in a darker shade of blue. Now, the trick to evaluating this summation is to notice the direction of the unit normal vectors, which I've called n. And remember that the unit normal vector always points out of the volume or the cell that we're considering. And so that means along the x-axis, the normal vector on the east face has a value of +1. It's pointing in the direction of positive x, whereas the unit normal vector on the west face is pointing in the opposite direction to the x-axis. So it takes a value of -1. And that allows us to evaluate this summation in 1D, as you can see there in equation 31. We've got rho UA on the east face and then minus rho UA on the west face. And many of you will be used to this simple form of the continuity equation from your earlier studies in fluid mechanics. You've got rho UA, of course, is the mass flow rate. So the mass flow rate on the east face has to balance the mass flow rate on the west face so that we can conserve mass in that cell. And some of you may have noticed that if you just look at equation 31 for the mesh we're considering, our mesh is uniform, all the faces have the same size, and our density is constant throughout for this problem. So we can see that the area on the west face is equal to the area on the east face, and the density on the east face is equal to the density on the west face. So that might imply that equation 31 has an obvious solution, which is the velocity on the east face has to be equal to the velocity on the west face. And that is true. That wouldn't be a very useful solution to our problem at this stage, because that would just end up with the solution of our Navier-Stokes equations being uniform velocity throughout, and then we'd have a very trivial solution for the pressure gradient, which wouldn't be very useful for us because we couldn't see where the checkerboard oscillations are coming from. But of course, what I want you to think about is that there is still an interesting solution to this problem. And the way to understand this is if you consider a very, very long channel, which has equal area at the inlet and at the outlet, then of course this channel overall will have equal velocity. The velocity coming into the channel will equal to the velocity exiting the channel, much like our 1D cell. But of course, if we have a body in the channel or some kind of obstruction, then this body will be providing a drag force on the channel, and then of course we'll have a pressure gradient on that channel. And so what's going to happen is that the pressure gradient will actually have to balance the drag from that object. And so we can still have an interesting solution to this problem. even though the velocity entering our cell or our channel is equal to the velocity leaving the channel, the pressure gradient will have to balance the forces on the body. So there is still an interesting solution to this problem that we're going to be looking at. So let's go back to that continuity equation for the 1D cell that we considered. And the next point to notice with this continuity equation is exactly the same factor that we had for the momentum equations before. That the continuity equation here is expressed in terms of the velocity on the faces of that cell. So the east face and the west face of the cell. But remember, just like before, we need the values at the centroids. So that would be U with a capital E for the subscript and U with a capital W for the subscript. And of course, there are, exactly as we saw before for the momentum equation, there are multiple ways of doing this interpolation. And the key point to notice in this part of the derivation is that normally in the CFD code, we solve the momentum equations first, so we have a solution for the velocity field, and then we solve the pressure or pressure correction equation afterwards. And so what that means is that we already know the velocity at the cell centroids, and so we don't have to use something like upwind differencing here, and we can just go ahead and use linear interpolation. And equation 33 gives us the linear interpolation form for the velocity on the east face of the cell and the velocity on the west face of the cell. And what we can then do is substitute those into the continuity equation. Now, at this stage in the talk, we've set up all of the conditions that are necessary for checkerboard oscillations to appear. We've used that form of the pressure gradient where we've used linear interpolation to get the pressure on the faces of the cell, and we've also used linear interpolation to calculate the velocity on the faces of the cell. And what we're going to see is when we combine both of these together, that's what causes the checkerboard oscillations to arise. So substitute in equation 33 into equation 32 and do some rearranging. We arrive at equation 35. And what you'll notice is that those UP terms, the velocity at the centroid of the cell we're interested in, cancel out. And we've now got the velocity at the centroid of the cell on the east and the velocity at the cell centroid of the cell on the west, UE and UW. They of course are going to have to be equal. But the final thing we can do here is we can now substitute into the continuity equation the momentum equation that we derived before. And for those of you who've seen my talks on the simple algorithm and the piezo algorithm, you'll recognize that this is what we always do to derive an equation for pressure or the pressure correction. We substitute in the momentum equation into the continuity equation, and this allows us to arrive at equation 36. And you'll see that now we've got those pressure gradients in there, partial P over partial X. And the final stage in this process is to substitute in the linear interpolation form for the pressure gradient that we derived before. And what happens is that we arrive at equation 37. Now, so far in this talk, we've done quite a lot of maths and we've done quite a lot of derivations and rearranging things, and it appears quite complicated and it's easy to get lost along the way. So what I'm going to do first is just remind you of what equation 37 actually represents. Equation 37, in the way we've derived it, is actually an equation for the pressure at the centroids of those cells. And you can see that in this equation, the unknown is going to be P with the subscript capital P. That's the pressure at the centroid of that middle cell, which you can see there. And what does that pressure depend on? Well, it actually depends on the pressure in the cells that are two spaces either side of the cell. PEE, which is east-east, and then PWW, which is west-west. So you can see that the pressure gradient here is coming in, and we're only really depending on the pressure two cells away from the pressure we're interested in. And then of course the UE tilde and the UW tilde were what we saw before. They were the momentum and diffusive fluxes into the cells on the east and west of the cell we're interested in. But the key takeaway from this point is you can see clearly this is where the checkerboard oscillations are arriving from, because the pressure at the centroid of cell P doesn't depend on the pressure in cells P, W and P east. There's no link at all. You could have any solution for the pressure in those cells and it wouldn't affect the solution in that central cell. And so what this means is that actually you can have two independent solutions for the pressure field. And what will happen, of course, is that if you were to plot along a line through those cells in the mesh, you would see both the independent solutions, because the pressure at the centroid of cell P will only depend on the pressure that's 2 cells away. Likewise, if you look in PE, that will only depend on the pressure 2 cells away. And so because you've got this two independent solutions, if you plot along the line, you will see what look like oscillations, but are actually picking up two independent solutions. And what we've considered so far, and the derivation that I've done, is only for the 1D form of this pressure equation. But you can quite clearly see where these two solutions are and where they might exist. Now, if you were to repeat this in 2D, of course, what you would find is that the pressure at the centroid of the cell you're interested in only depends on the pressure in the cells 2 units away along the x-axis, but also 2 units away along the y-axis. And so what ends up is you can have a pressure field which has a checkerboard or a chessboard-like appearance in 2D. And this is because we've got two solutions effectively superimposed on top of each other, which as a user, if you look and plot the field as contours, you'll see this appear as what are called checkerboard oscillations. So now hopefully, I know there's been a lot of derivation so far, a lot of mathematics and a lot of rearranging, but you can probably see how the checkerboard process can appear, and that actually it's rather independent of things like the discretization procedures that you use in the momentum equation, and whether you have source terms or unsteadiness. The checkerboard oscillations have a tendency and they can appear. However, of course, we don't want these checkerboard oscillations to appear. That's the key thing in our CFD solution. We don't want these oscillations to appear. And so for a developer of a CFD code, you need to choose a method of preventing these oscillations from appearing. And what I'm doing in this series of 3 lectures is focusing on 2 different options which you can use for ensuring that these checkerboard oscillations don't appear in your solution. And the 2 options are given here in the diagram on the slide. You can either use what's called a staggered grid, or you can use a special form of interpolation, which is often called Rhie Chow or Rhie Chow type interpolation, which is named after the 2 authors who proposed a special method of interpolation fairly early on in the development of the CFD method. And what I'm going to do is address these 2 methods in more detail in the next 2 talks. And so you'll by the end of this series of talks, you'll have a good example of where the oscillations can arise from, but also what are the methods for suppressing them. And then you'll have a better understanding of how your CFD code works to suppress and prevent checkerboard oscillations. Before finishing, I also want to make the small side point that there is a third method of preventing these oscillations, and that's called artificial compressibility, where rather than treating the problem as truly incompressible, you treat it as a special form of compressible flow. But this method is far less popular, and so I'm not going to be doing a look at this in the series of lectures that I'm going to be presenting on checkerboard oscillations. So just to wrap up the talk, the key points here is that checkerboard oscillations can arise when we're using a segregated solver, which is pressure-based for incompressible flows, which are often the majority of flows that we consider in engineering and scientific applications. And the checkerboard oscillations arise from 2 causes, and you need both of these causes to be occurring as well for the checkerboard oscillations to appear in your solution. And that is, they can appear when you have collocated storage of the velocity and pressure fields, which means the velocity and pressure are both calculated and stored at the cell centroids. And you use linear interpolation of the velocity when the pressure equation is formulated. And you need both of those factors together for checkerboard oscillations to appear. And there are 3 different methods which I've introduced for preventing or suppressing these oscillations, and they are staggered grids, artificial compressibility, and then Rhie Chow type interpolation to correct and remove these oscillations. And what I'm going to be doing over the next 2 videos is considering these methods in more detail. So that brings me to the end of part 1 of this 3-part lecture series. I'm really hoping that by the end of this part 1, you'll have a good understanding of what checkerboard oscillations actually are and how they can arise in the CFD solution process if we're not careful with the discretization methods that we use when we're setting up the equations. I know there's been a lot of mathematics and derivation in this talk, so I'd really like to hear from you in the comment section. How useful did you find it? Was it easy to follow? Are you looking forward to the next 2 parts in this 3-part lecture series? So in the next part, we're going to be moving on to looking at staggered grids, which I think you're all going to find really interesting because you'll also understand and learn about some of the development and the history of CFD codes, and you'll start to get an understanding of where CFD codes are today and why they were developed. So I look forward to delivering that talk to you. It should be out in a few weeks' time after this one's delivered. But until that time, I really look forward to hearing from you in the comments section. Let me know, how did you find the video? Are you looking forward to the next series of talks? And I really do appreciate your continuing support with the channel. It really does mean a lot to me. So until next time, thank you all very much for watching, and I look forward to hearing from you.